So we've computed using differential equations the density of 2 and 3 variable clauses as a function of time. Now we need to think about the one variable clauses, the unit clauses. Those are the ones that if they proliferate, if they get to, say, square root of n of them, then we're going to have a contradiction and the algorithm will fail. How are unit clauses created and destroyed? Well, they're destroyed when we satisfy them, when we give them the value of their variable that they want. They are created out of two variable clauses. So suppose I have a unit clause which wants x to be false. And then over here I have a two variable clause which says it wants x or y to be true. Well, as soon as I satisfy this unit clause setting x false, this two variable clause becomes a new unit clause demanding that y is true, because that's the only other way to satisfy it. So I'm not sure what the right metaphor is here. The two variable clauses are midwives or hosts of parasites or something, but this is the life cycle through which new unit clauses are born. What we need to do is compute what some would call the branching ratio and what others would call the reproductive number of these unit clauses. Think in terms of an epidemic. If the average number of new cases of a disease infected by a person with that disease is less than 1, then you'll just have little outbreaks of the disease that are isolated from each other, just like those small islands we saw below the percolation transition, or in some sense like the small islands of the minority point of view in the Ising model. On the other hand, if the reproductive number is bigger than 1, then the unit clauses will proliferate. We'll get an epidemic of them. They'll quickly get out of hand until two of them demand opposite things from the same variable, and we'll have a contradiction. So we need to compute this reproductive number. Let's call it lambda. Well, it actually looks a lot like the terms in our differential equation. The density of two variable clauses controls the overall rate, and the probability that one of these two variables is the one which is going to be set next is 2 divided by 1 minus t, again with that factor of n. Moreover, because both types of steps the algorithm does essentially give this variable a random value, the probability that it disagrees with this two variable clause, creating a new unit clause, is 1/2. So lambda, after we cancel out these 2's, is just s2 over 1 minus t. But we figured out what s2 is as a function of t using our differential equations. So we go back up there and check, and we find that lambda is 3/2 times alpha, proportional to the density, times t times 1 minus t. So again, the question is lambda always less than 1 throughout the algorithm? If that's the case, then we'll at least have a good chance of handling them all, satisfying them all before they proliferate. On the other hand, if lambda is bigger than 1, it'll be like the Hydra from Greek myth. Every time we chop off one head, a bunch more grow in its place, and pretty soon they proliferate, and well, the heads of the Hydra didn't contradict each other, they just tried to eat our hero. But anyway, you know what I mean. So what we need to do is see if lambda is less than 1 for all values of t. Well, because lambda is proportional to t times 1 minus t, that's a quadratic function. It starts out at 0 when t is 0, and then it goes back down to 0 when t is 1. It's maximized when t is 1/2. It turns out that the moment of greatest danger for the algorithm, when the unit clauses are proliferating the most, is when we've set about half the variables. At that point, we plug in t equals 1/2, we find that lambda is 3/8 times alpha. Well, great. If alpha is less than 8/3, which is about 2.6, 2.7, then lambda will be less than 1 for all t, and the algorithm will succeed at least some of the time. But if alpha is bigger than 8/3, then at that moment of greatest danger, lambda will be bigger than 1. We will have a supercritical epidemic of unit clauses, and the algorithm will fail. So what have we shown? We've shown something about the phase transition in its own right, but we've also shown something about an algorithm. So we've shown that alpha, the critical value of alpha for 3-sat, is greater than or equal to 8/3, about 2.6. But we've shown this in an especially nice, constructive way. We haven't just shown that solutions probably exist. We've actually shown that a particular algorithm succeeds in finding them. Why do I say constructive? Well, in mathematics, sometimes we have non-constructive proofs. Proofs that work by contradiction, that say, well, such and such a thing must exist because if it didn't, there'd be a contradiction. Well, that's a nice thing to know, but that kind of proof gives us no information at all about where this thing that exists is, or how we might find it. It just means that it's impossible for it not to exist. And indeed, there's been a long-term controversy within mathematics about whether that kind of proof is really a proof. Strict constructivists would say, well, no, that's not even, that doesn't count as a proof. I want to actually see the thing you're talking about. You must tell me where I can find it. Indeed, you can think of computer science really as the branch of mathematics that tries to figure out better and better ways to actually find things. And in that sense, theoretical computer science is trying to unfold and elaborate the notion of a constructive proof that things exist. All right, so if you generalize the same argument to k-sat, where there's k variables per clause, guess what? You can efficiently find solutions up to a density which scales as 2 to the k over k. That's interesting. But remember that the true threshold is about 2 to the k. So what this says is that the density up to which we know how to actually find solutions is a factor of k below the threshold up to which there are solutions. There is a cleverer algorithm that uses a kind of local search developed by Amin Kojo-Oglan, which does a little bit better. It gets up to 2 to the k times log k over k. But that's still far below the true threshold. So there's this big zone all the way in between roughly 2 to the k over k and 2 to the k, where we know solutions probably exist, but as far as we know, there is no polynomial time algorithm that actually finds them. So the upshot of all of this is that we think this range of densities gives us hard, random examples of SAT. Problems where the formula is satisfiable, but where it's hard to find a solution.